Hey LBW, what's up? Hi, just an other old. Hi, just another old. Hey, Skugget. Oh, really? Hey. Bro. What is that? What how does that work, Crow? What is that? Oh, Crow is teacher's pet. Wow, incredible. Tell me more, Crow. Oh, let me make sure my pencil. Oh, I see. Oh, I see. Ah, okay. How did you try it? Did it go well? Oh, wow. Congratulations. That's incredible. Really good. Incredible. Yeah, I bet. I bet it was. Oh, was that enough time for you? Like, how do you think you'll do for the next one? Are they the same difficulty, but like more problems, or they increase the difficulty as well? Oh, really? Oh, okay. Okay. Hey, man, round one is good, man. That's great. That's really good. Ah, easy is a relative term. Yeah. That's wonderful. That's really cool. Hey, maybe you'll get one. Just try your best. Who knows? Are these things like every year or? Ah, that's the smart way to do it. Just another. Yeah. That's the. Hey, AC, what's going on? Alright. Okay. Oh, awesome. Alright, let's see if we can get this show on the road. Okay. Okay. So what's going on here? Okay. What am I teaching? Oh, yes. All right, so this is intersection theory. This is a worldwide seminar attended by 5 people. Some are here in the States. 5 minus them are in Australia. What's our task? That's right. What's our task? Our task is to become fluent with the mathematics that surrounds the topic of intersection theory. Enumerative geometry. That's the name of the field. And it's filled with, it's got this charming nature of being, the problems are very concrete and simple to understand, yet the solution technology requires basically an understanding of at least the history of algebraic geometry, which is one of the biggest chunks of modern mathematics. Okay, so today I want to give you, we're going to start the path to the main definition, which is, that's later, M9 easy, that's later. Main definition is that of the Chow ring attached to a smooth projective variety, or smooth variety in general. Denoted A of X. All right, that's the main object that one studies or uses when trying to figure out answers to enumerative problems. And so today I hope to at least state what the definition is of this ring, this object. Okay. But to get there, we'll take the historic route, or a motivating example. Motivating example and the sort of basic first instance of a hint that there might be something like a Chow ring in the background is Bezou's theorem. I'll talk about that, what it is, what it says, its incremental generalizations, how those generalizations led to the development of modern commutative algebra, in part, and then a massive generalization. In fact, the massive generalization of Bezout's theorem sounds weird, but the massive generalization of Bezou's theorem is the Chow ring, that it exists. Okay, A of X exists. That's a massive generalization of Bezou's theorem. Okay, so let's do that. Let's talk about Bezou's theorem. Here's Bezou. The theorem is credited to Bezou, but a rigorous proof didn't emerge until the 1900s. Okay, so and Bezou was in 1700s, so I'm not sure. It's one of those things. Okay. So Bezou's theorem. Probably a version you've seen in an elementary algebraic geometry class. Okay, so let D and E be two smooth curves E2, which meet transversely. Then they meet at D times E points. Where D equals the degree of D and E equals the degree of E. All right. No, Ramanujan gets enough credit for good reason, but here this one is sort of more like an empirical observation than yeah. This one is a little bit less solid. Okay. Okay, so this is the statement. Now there's some important assumptions. Important assumption is that we work over an algebraically closed field. Okay? That's one important assumption. The second assumption is it's in the statement. It's P2. Data problems? What does that mean? Is there a problem? So I want to point out a couple things. We're going to talk about all the assumptions here. P2 is needed, is in the statement, not A2, like your affine plane, you know. It's not R2, it's more like C2. Not C2, it's CP2. And meeting transversely, apparently, is in the statement. So this is the ancient Bezou theorem that you first see. So all you got to do is witness some examples that show you that these things are necessary. So for instance, you see two ellipses. So now you look at examples that illustrate the importance of these hypotheses and why we're going to continue to keep those hypotheses forever. Why algebraically closed field? Exactly. For instance, if you look at two real ellipses, or no, you don't even have to, but an ellipse and a line. Okay. So they don't intersect. There's no real points of intersection. But sometimes there's two, which is what's predicted. This is predicted, And this is a bit of a mystery. Where did the points go? They're still there. It's just complex numbers. Yeah? It's just you got to pass to the algebraic closure of the ground field. So that's what we mean when we say points, by the way. Points mean naively points in P2 with entries in your ground field. So you have to make sure you're over an algebraically closed field. Classic reason why that's important. And of course, why P2 is the usual reason. This is actually the reason why P2 is invented in the beginning. It's that you can have two lines meeting at a single point, of course. That's 1 times 1 is 1. So Bezou seems to be correct here. But then you just swivel the lines and sort of just rotate this line down. And you get two parallel lines. And then the point is somewhere. Point has gone. Solution has escaped the variety. Yes, exactly. That's actually this example after a coordinate change. Yeah. Megalomorph. That's the first example after a coordinate. Okay. So that's why P2. And so this somehow P2 is keeping solutions from escaping. Algebraic closeness is giving you enough solutions. And now transversely has a meaning. It means that since these curves are smooth, at every point there's a well-defined tangent line defined by partial derivatives in the usual way. Those tangent lines need to be distinct at every single crossing of D and E. Now, why is that necessary? It's because example 3. The number of points is 2. Is 1, but it's supposed to be 2 points if you just read the last sentence. So number of points is less. So if we give up focus on geometric point, we still have a chance to discuss then over arbitrary field. Yes, over an arbitrary field, if you extend what you mean by a point, yes, a point meaning a closed point, and then each point is counted with the multiplicity, which is the field extension over which it's defined. Then it's still true. Then you still get D times E counted with that multiplicity. You have to count the multiplicity of that point according to the extension of the field that's required to define the point. Does that make sense? Yes, using that pure scheme theory language, you get a generalization. And so speaking of generalizations, you get the next thing that people observed was that you can do a little better. You can relax the transversality clause. You can relax the transversality clause. You can relax it to just which meet at a finite set. But the trade-off is that you have to add a clause, a curious clause. you have to add a clause here. Counted with multiplicities. And now this is where the history really begins. Because what happened was basically people had some intuitive notion of what intersection, the amount of tangency of intersection that two smooth curves have at a point should mean. They had some intuition. And the intuition was basically, if you were to wiggle one of the curves, you would see some number of transverse intersections for the nearby configuration. And those transverse intersections would all merge. So that one fixed number, called the multiplicity in retrospect, will merge to form the tangential intersection. Okay, so in this case, it's kind of like you wiggle the line a little bit and you see two transverse intersections. And so therefore, we should just give this point the intersection multiplicity 2. All right, so given that was the first way that people learned how to assign points with numbers attached to the point. And so that the weighted sum stays d times e, and rescuing this beautiful theorem. Okay, so there's a way to incrementally generalize, and at each stage you learn something. You learn an idea. And here it's the idea of two curves and their intersection multiplicity. Okay, I didn't tell you the definition of that thing because the definition is doesn't come out in just one line. But it's easy enough for smooth curves. It's the definition is totally believable and easy to point to. If you simply locally parameterize one curve using... Hey, what happened here? Bezou just magically showed up. Okay. All right. So let's not talk about that. It's believable that there's some systematic way of assigning multiplicities when two smooth curves meet tangentially. Okay. But what's even crazier? Who's that? That was Bezou. This is stuff with DVRs, local parameters. Yes, exactly that. Megalomorph, exactly that. Okay. So next, you could actually... Why does Bezou keep popping up? It's because I have it... Anyways, okay, here's Bezou again. So you can generalize even further. By relaxing that the two curves be smooth. That's right, Megalomorph. He's intersecting our stream with great multiplicity. Okay, you can relax further and assume that and just say D and E are two curves of degree D and E. And one of the sort of main technical difficulties here is, how do you systematically assign intersection multiplicity now? Whatever intuitive method you had before, how does it survive this situation? I don't know, two curves meeting. And notice they are both singular, say, at this one point of intersection. How much does this point count? Do you have a systematic way of assigning multiplicities to intersection points, which saves the theorem. And the answer, after the efforts of many, many mathematicians, is yes, there is a notion of intersection multiplicity of two curves in P2, which doesn't reference Bertini. It's not circular. A purely commutative algebraic way. You give me the two defining equations and the point of intersection, you can assume is the origin, and out comes a number using purely commutative algebra, ring theoretic calculation. So there is answer. Yes. It's called the intersection multiplicity of D and E at P. Okay, so there is a way to attach intersection multiplicity even to this gnarly situation in such a way that if you count now the points with this multiplicity, which has this multiplicity has nothing to do with Bezou's theorem, it's just a pure, well-defined computation. When you count the points with multiplicity, you still get D times E. That is an even better version of Bertini, and you still it's marvelous that such a constancy continues to hold. All right, so it's what's marvelous is the constancy. You get D times E no matter the pair of curves. As long as they intersect at a finite set. Okay? D times E no matter the pair of curves. Let me tell you why this is marvelous. Suppose you had to solve some simultaneous system of equations. Where this was some degree D homogeneous polynomial, and this was degree E. And each one defined, let's say, a smooth curve or whatever. Irreducible curves, each one irreducible, let's say. And you were asked, hey, how many solutions does this system of equations have? You know, problem in enumerative geometry, classic problem. Well, if you already knew the constancy phenomenon, that the F and the particulars of the F and the G don't matter. If you already knew constancy of finite intersection number, you had this principle in your mind. Oh, then you can just take F to be a product of linear forms, general ones, and G to be a product of other general linear forms. In other words, you can take some complicated intersection between two very complicated curves. Okay, that's not a curve. And you can trade away F and G for, say, a union of lines. And then you just count in the obvious way. Oh, you get 1, 2, 3, 4, 5, 6. 6 solutions. 6. This has 6 solutions. Counted with multiplicity. You see? That's insane. In other words, you're not telling me anything about the solution set. You don't know anything. It's impossible to solve high-degree polynomials. We learned that in Galois theory. You're not going to get there using simple methods, just the exact solutions. But the number of them, if you knew this constancy principle, you could deduce. You could teleport knowledge about this system of equations. You can continue your knowledge of this simple system to the one that you were initially asked about. It doesn't tell you the locations or anything. It tells you how many. So the fact that the number is constant is marvelous. It's crazy. It's saying that this has 6 intersection points because this one has 6 intersection points. There's a constancy counted with multiplicity for the number of intersection points between two curves in P2. All right? Now, it's not true that in general, always in algebraic geometry, when you have a situation, a system of equations that are giving constant number of solutions, or an enumerative problem where there's constancy, or where you have a situation where you have a finite solution set, that when you perturb things, you'll get a constancy of intersection number. It's not true in full generality, but it is true in many, many contexts. The key word here will be that something involved, the subvarieties involved, will have to be sufficiently nice. The technical condition is that one of the varieties, actually both, have to be Cohen-Macaulay. But that's relatively mild for most intersection theorists or enumerative geometers. So this constancy principle, I want to say, is going to be very, very general. All right. Awesome. So this is first hint that there's some kind of there's a number that's a product of two numbers that were attached to the curves, the degrees of the individual curves. You just multiply them and you get the size of the common intersection set counted with multiplicity. Okay, so that's Bezout's theorem, and Bezout's theorem is like a first instance of what's called a Chow ring calculation. You can think of Bezout's theorem. You can think of Bezout's theorem as saying, instead of the curves D and E, start equating two curves if they just have the same degree. So the specifics of D and E don't matter. Only their individual degrees matter. And when I say they don't matter in the context of figuring out how many points they intersect at. Okay? And so, is there a systematic way of taking subvarieties like D, D is a subvariety of P2, or E's, and declaring equivalent this crazy cubic and these three lines, equivalent for our purposes, or this conic here with this very degenerate conic, the union of two lines. Is there a way of just declaring them to be equivalent systematically and work not with particular varieties, but with their equivalence classes and still maintain a cohesive intersection number that survives the equivalence relation? That is the goal of the Chow ring, and that's exactly what the Chow ring achieves. So the Chow ring answers this question: is there a way, a systematic way, to mod out by an equivalence relation which says one curve of degree d is just as good as any other curve of degree d, and one curve of degree e is just as good as any other curve of degree e, but that the equivalence relation preserves the intersection number? Is there a way to mod out by an equivalence relation here and construct a ring that represents this theorem? The answer is yes. It's called the Chow ring, and we're going to talk about it now. All right, so the Chow ring begins with the concept of the Chow groups of any algebraic variety. Singular, smooth, doesn't matter. Okay? So the first thing we need to understand is the concept of the Chow group. So if X is a variety, any variety, and for us, variety means irreducible. Okay? So it in particular has pure dimension. It has one particular dimension. There's not several components, etc., etc. So X is any variety. Then there's something called the Chow groups of X. So now fix a dimension. So X is any n-dimensional variety. Fix a dimension. K that's smaller than or equal to n. And now what you do is you try to write down every subvariety first, and then mod out by an equivalence relation, very much like one curve of degree d is the same as any other curve of degree d. That's the idea. Okay, so you fix the dimension, and you consider subvarieties. So each when I say variety, I mean irreducible. Okay, so you look at the set of all subvarieties of dimension k. And subvariety means closed subset. Just imagine full set of all of them. It's enormous. It's a completely out of control set. This is. Can't possibly be useful. It seems like it's completely not going to be usable in any given situation. And that's true. That's true. It's not going to be a very useful concept at this level. But what you do next is you create an algebraic object out of this. Something like a group, right? An operation of adding. And so the way you do, typical thing you do is you take the free abelian group generated by them. They start with this. Free abelian group generated by the set of subvarieties of a given variety X. This is a monstrosity. Okay? Completely, don't be confused. It's a very simple thing. How to define an element of this. Just take z-linear combinations of subvarieties. Now, for each variety, you write bracket y for the generator that it produces. And this first abelian group is called the group of k-dimensional cycles. It's typically denoted z sub k of x. The group of k-dimensional cycles. So a cycle is simply a formal linear combination of subvarieties of dimension k, of some fixed dimension that you're studying. Okay? Great. Then we're going to mod out by that promised equivalence relation. Hi, thanks for the follow. Okay, what is this equivalence relation? I need to motivate it just a second. Because actually at this stage, there are several different equivalence relations. And for our purposes, the other ones that you'll learn about, if you're over the complex numbers, there will be another one. There's another one that's numerical equivalence. All of them will serve our purposes in intersection theory. Okay, but the one that's like the most purely algebraic, really, is the equivalence relation called rational equivalence. Okay. Okay, now what is rational equivalence trying to say? I'll explain the words. Rational in geometry, not number theory, in geometry, in not arithmetic, geometry, okay? Classical algebraic geometry. The word rational means parametrized by free parameters. Because it's talking about that word rational is pointing at the rational function field, the pure transcendence field with some number of parameters. That's what the word rational means in the very geometric setting. Okay? And for us, what rational means is P1. One free parameter. Okay? Or A1, it's not going to matter. One free parameter. And so the idea here is we'll say two subvarieties are rationally equivalent if there is a free one parameter family of subvarieties that interpolates from one of them to the other. So in words, it means there is a free one parameter family. So that just means a family of varieties parametrized by P1. Parameterized here is talking about the family, so labeled. Interpolating from one k-dimensional subvariety to another. Why does it feel so much like homotopy equivalence? It's because it's basically motivated by that. It's trying to mimic that story, but it's trying to stay algebraic. And so the compromise is don't use intervals. Intervals are, what the hell is an interval? don't use intervals. Use P1 or A1. You can use A1 too, doesn't matter. All right? Use P1 as your interval. Okay, so let me write it out more carefully. So suppose y1 and y2 are two subvarieties of dimension k. No, that's a different thing. That's a different thing. I believe that's a different thing. Yeah. Okay. They might be related, but I think it's much fancier, that thing. The A1 homotopy thing. All right. Okay, so you have two k-dimensional subvarieties of x. And now what you do is you require that there be a k+1 dimensional subvariety which contains both y1 and y2 such that, so this is one way of talking about rational equivalence. So such that there's a rational function on W in the function field of W where the divisor of zeros is y1 and the divisor of poles is y2. Now the divisors of zeros and poles of a rational function are well-defined codimension 1, typically, subsets of a given subvariety W. So there's like a definition for what the zero divisor and the pole divisor of a rational function are. But if you don't like this one, there's an even more geometric one. There's an alternative you can choose. It's in a sense it's cleaner. So we'll say y1 and y2 are rationally equivalent if two subvarieties. Okay, two subvarieties are rationally equivalent if there is a subvariety of the product let's call it W. We'll call it W again. Okay, well, W in the product. There's a subvariety of the product such that W is not contained in any fiber over P1 so that's like a T cross. It's not contained in any fiber. And such that there exists 2 points on P1 with W intersect that fiber is Y1, and W intersect the second fiber is also is Y2. And these equalities are equalities as schemes. Okay, so let me draw a picture that you might see in the book. We'll say Y1 and Y2, two subvarieties of dimension k, are rationally equivalent if you can interpolate from one to the other using a bigger subvariety. W is a variety. Subvariety. Irreducible. Okay? Good question. If you don't say W is irreducible, you could just place anything in any fiber, and suddenly rational equivalence starts to look very useless. Okay, now slight generalization of this concept is that you can say 2 cycles Okay, so this is what it means for two irreducible subvarieties to be rationally equivalent. But the rational equivalence notion can be extended slightly in the following way. So suppose you had that the preimage for a third parameter, T3. I'm just going to call this pi inverse of T3 intersect W was, as a scheme, was the union of several varieties. A1, okay, what if that over some third point the fiber was the union of 3 varieties as a set? Well, given our hypotheses on the types of algebraic varieties we're considering, it's all finite type. It turns out that any scheme of finite type over K has concept of irreducible components and the length of each component. We'll talk about this probably next week. Okay, so there's a notion of irreducible components of a scheme. They correspond to minimal primes in a primary decomposition. And each one comes equipped with a length. The length is going to be what we call the multiplicity of that of that scheme along that component. All right, so as a scheme, if you have a reducible scheme, then each component comes equipped with a concept of its length. These are just positive integers. All right, so if a fiber is reducible, is a reducible union of has to be dimension k subvarieties, because you're imposing one equation, one non-zero divisor on a ring, and that drops the dimension by exactly 1 by Krull's ideal Bezout'S. So each of these AIs are k-dimensional. You're imposing one equation on a ring, non-zero divisor. So these are each k-dimensional subvarieties. But the point I'm trying to make is if you look at their scheme, the scheme cut out by T3 equals 0, or T equals T3. The scheme carries the information of the length of each component's, the length that each component counts as or has. Lengths are numbers that we know how to attach to irreducible components of schemes. And so the full rational equivalence notion is that we then say that any two of these fibers are rationally equivalent as cycles. Okay. Have fun, just another old. Okay, so rational equivalence is use P1 as an interpolator parameter and take scheme theoretic fibers of k plus 1 dimensional subvarieties of the product and declare those fibers as equivalent to each other. Where how many times do you take each component in a fiber? You read off this length, which is a purely commutative algebra computation at the minimal primes in a primary decomposition of the given ideal. Okay, the ideal here is T minus T3. Principal ideal. T minus T3 on every affine chart. Okay? So that's the notion of rational equivalence between two irreducible subvarieties, or in more generally, positive linear combinations of subvarieties. Okay, and now what you do is a little bit subtle. Okay, so subtle. There's a subtle thing here in the definition. You let the Chow group be the set of cycles, the free abelian group of cycles, modulo, and this is important, modulo the equivalence relation generated by those cartoons. Generated. Okay? In other words, you take the you take the subgroup generated by all differences y2 minus y1 or y1 minus this linear combination of a's over all conceivable w's. Does this make sense? You take that subgroup generated by those differences, and that's what you mod out by. All right? A little subtle point. The equivalence relation is an instance of an equivalence relation generated by some kind of building block ones. And the building block ones are, look at the product X cross P1. Draw a K plus 1 dimensional subvariety that dominates P1. Take scheme theoretic fibers and declare them, two of them, their cycle differences to be 0. That's the equivalence relation that's what rational equivalence means. Okay? So the reason why I'm saying this is that if you know one subvariety is rationally equivalent to another, another cycle using some W, and then you know that like that one is rationally equivalent to another one using some W prime, it's actually not the case you can find necessarily a W triple prime that interpolates perfectly from this one to that one. So it's important that you say equivalence relation generated by these fundamental cartoons. Okay, so that's what we're doing, and all we're doing. Listen, folks, all we're doing is we're taking the concept of any degree D curve is rationally equivalent to any other, and we're just naively porting that over to all dimensions in all ambient spaces. That's all we're doing. We're just taking the naive thing where you drag one variety by a parameter P1 and declare the other one equivalent to all dimensions in all conceivable varieties. Okay? More language. Instead of rational equivalence, you might hear the word, especially from me, linear equivalence. Now, maybe there's a technical difference. Not for me. Okay, so I'll just say linearly equivalent because a P1 is a line. That's why it's linearly equivalent. Equivalent according to a line, P1. All right, so that's the fundamental equivalence relation. And now I'll state the ultra generalization of Bezou's theorem. Two of these cycles are equivalent if we can go from one to the other in a series of interpolation steps. Even that one, I'm not sure is true. Because there can be negative coefficients that are required in order to get from one to the other. No, I don't think it's as easy as that. Yeah. It's not as easy as that. Yeah. Yeah. But like intuitively, you can go ahead and think that. But it's not so rosy. Yeah. Okay. Yeah. Okay, so I had to think about it, but yeah, it's complicated. All right, so here's the altered generalization of Bezou's theorem. All right, what it is it's I'm just going to state it. It's it's not that one. It's right here. Yes. There we go. Here we go. It's theorem 1.1. Okay. So to set it up, this is the last thing I'm going to say today. But to set it up, so now suppose X is a smooth variety. And now, here's the statement. If A and B are subvarieties, which intersect in the correct dimension, okay? If you have two subvarieties which intersect in the correct dimension, and if you think about it, this makes sense, right? Codimension of the intersection ought to be codimension of A and then codimension of B, right? Slicing intuition. Okay, you won't get a negative coefficient from a fiber of a map. That's correct. You won't get that. But yeah, that's true. But there's a technicality that we have to worry about in Lycolog's question that involves the possibility of negative coefficients. Anyway, I don't want to talk about it. Okay, so if A and B are subvarieties of X such that the codimensions of the intersection is expected, is the one that's expected, then we can attach numbers. We can attach to each irreducible component of the intersection a number m sub ci and for technical reasons it'll also be technically dependent on the subvarieties A and B. That's for technical reasons. I'm not going to be present if A and B are Cohen-Macaulay. That's exactly the kind of technical stuff that we will face. To each irreducible component, a number such that a number. So then we can, number one, attach to each irreducible component a number. Two, we can also impose an intersection operation, a multiplication. On what's called the Chow ring, which is the graded ring you can create a product structure, like a multiplication structure, making this into a ring. in such a way that 3. When you take A's element in AX and multiply by the class of B, that's the word for it, the class of B, you get another element in AX, because I said there's a way of putting a ring structure on this thing. But you get compatibility. You get that this is the sum of those multiplicities times the classes of the intersection components. That there exists an intersection product on the Chow groups, making it into a ring, which further looks like, well, you should take intersection multiplicities and take the individual classes of the intersection components. That there is a compatible way of making an intersection product with what you would naively hope is the answer cycle. That is the massive generalization of Bezou's theorem. The existence of both a way to attach intersection multiplicities to irreducible components of an intersection, and a separate way of assigning a product of two classes that you can make those, you can bring those into alignment, is a massive generalization of Bezou's theorem. Okay, so there is this basic fundamental fact which we'll be exploring as we go. Okay, yep, see you, Skugget. Yes, the dimension is the top number, and that's the k equals 0 is the bottom number. All right. So if you have a smooth variety, there's a way to put a multiplication operation on the set of the direct sum of all Chow groups. And the content here is, if two subvarieties A and B intersect correctly, then the answer of their intersection product in that ring is in agreement with what you think it should be, as long as you sit down and work out how to put the right numbers right here. That is the ultra generalization, and I hope you see it, sort of the Bezou theorem that started in the 1700s. Too small letters. I had to zoom out so that you can see the whole thing on the page. Okay, great. We'll talk about this more and more as we go. It's not easy material. So Wednesday I'll start with this. I'll write out why this is Bezou's theorem in the case of P2, and then we'll talk about the Chow ring and how to manipulate, how to understand a Chow ring in very simple examples. So the next thing is that's basically what is the Chow ring of P2, and then point to various things in this formula and say that that's what Bezou's theorem said. And this is and then we'll talk about Chow rings and how they behave under simple operations on varieties. his binoculars. Well, for me, it's not so zoomed out because I'm looking at the screen here. So, okay, can we together work on Chow ring of P2 just for fun? Like when did you want me to talk about that? Now you want to see the Chow ring of P2? Okay, we'll figure out the Chow ring of P2. Okay, so the first thing is that A sub 2 of P2 is just Z. Okay, why? Z sub 2 is the set, the free abelian group on all two-dimensional subvarieties of P2. No, Z2, oh yeah. Subscript means dimension, superscript means codimension. Exactly. So subscript means dimension of cycles. And if we use superscript, it'll mean codimension. Important notational thing. So Z2, well, you gotta list all the subvarieties of dimension 2 in P2, which is irreducible. So you're always just gonna get Z generated by the class of the variety itself. It's called the fundamental class. So the top highest dimension cycle group is generated by a single element called the fundamental class. Okay? And now, if you look at the equivalence of, if you look at rational equivalence, there are no elements in the subgroup that you're supposed to mod out by. Because you're supposed to produce a k+1 dimensional subvariety of the product. And you're supposed to declare one fiber equivalent to any other fiber. And then generate the subgroup of differences. Well, a k+1 dimensional subvariety of this product is the whole product again. I'm telling you the general story for all dimensions. And so the rational equivalence is P2 minus P2. The group generated by this is clearly 0. And so you just get Z with P2. So it's one copy of Z. And this is true generally for X, any irreducible variety X. And that's what we're always talking about here. Okay, so now A1. Wait, is that a joke? Is it useful? I don't know. Okay, A1 now. First, you need to write down every one-dimensional subvariety. Every one-dimensional this is going to be tricky. Every one-dimensional subvariety of P2. This one's going to be trickier. Hey Twitch, let's go. How's it going? Okay. Now, what are the... So you have to have knowledge of what the one-dimensional subvarieties of P2 are. I'll tell you what they are. They are irreducible curves. Subvariety, right? Yeah, that's all homogeneous equations conceivable as long as they're irreducible. You say subvariety, the word variety, according to our conventions. That's right. Oh, thank you, Twitch. Thank you. That's that's great. Okay, so this is essentially the set of all curves, irreducible curves. Okay, okay. And now let's investigate the equivalence relation of the notion of rational equivalence. Okay. All right. How will I do this? Okay. So suppose let's understand one thing about P2 cross P1. If someone tried to give you a two-dimensional subvariety of P2 cross P1, why 2 dimensions? Because I have to go 1 dimension larger. Closed subset. Yes, exactly. Math online problem solving. Exactly. Yes, we'll get to it. Exactly. So suppose someone gives a two-dimensional subvariety of P1 cross P2. All right. That is a hypersurface in this three-dimensional variety, P1 cross P2. And there's actually one systematic way of writing down hypersurfaces in P1 cross P2. There's like one way. Just like there's one way of writing any hypersurface in projective space. You just put a degree D homogeneous polynomial, set it equal to 0. Okay? So that I'm going to use. I'm just going to use that as our as a fact. Okay? So there's only one to write down a variety, a hypersurface that is, you write down a bihomogeneous form with a particular bi-degree, your favorite. So if this is ST coordinates and this is x0, x1, x2, you have to write down for me a homogeneous form which has homogeneity in like the two separate sets of variables. It's both. Is it your hobby or are you working in this field? It's both. Okay. Okay, so let me give you an example. Like this. S times x naught to the dth power plus t times x naught to the d plus y naught plus equals 0. Example. Like this. This is a subset, well-defined subset. Codimension 1, because I'm setting one equation equal to 0. That's not a 0 divisor. in in a variety, on a variety. Okay, it's actually a section of a line bundle. This thing. All right, section of a line bundle. The line bundle is anyway, it's tensor product of O of D on P2's factor and O of 1 on P1's factor. Section of a line bundle is setting it equal to 0. Okay, boss. Awesome. Okay, and now, and this is irreducible. It doesn't factor. Okay. So now what you're supposed to do is, this is just one example. You can take other more complicated examples if you'd like. But what you want to pay attention to this. No matter what you plug in for S and T, you will always get a degree D, same degree, polynomial in x naught up to x2. And so what that means is that you will never have, even after you mod out by the equivalence relation, like the whole subgroup generated by rational equivalence, you will never have a degree D curves class rationally equivalent to a degree other than D curve class. So in other words, so if consequence of this is if C is rationally equivalent to D, if two curves, if you look at their classes, they're rationally equivalent, then the degree of C has to be the degree of D. Okay? Notice how the knowledge of how restricted you are in writing a codimension 1 subset of this product, that knowledge trickles down to kind of an invariance, that the degree has to be preserved under rational equivalence. Okay, a degree 1 line, a line is never rationally equivalent to a conic. Okay, so that's the first thing. Now the second thing is this. By using W's of the form S times x naught to the D plus T times f of where this is arbitrary. By using polynomials by subsets W defined by these kinds, you get particular rational equivalences. You get that the curve defined by the vanishing locus of f is rationally equivalent to D times the line defined by x naught equals 0. Why? Because look at this subset of P1 cross P2. Because at when you put in ST you get x naught to the D equals 0. Which as a scheme, as a divisor with multiplicity, as a codimension 1 set with order of vanishing taken into account of the defining equation, the order of vanishing of the defining equation here is D. So that's that length L sub I that I'm talking about. In this case, it's kind of intuitively obvious, but in general, you do a commutative algebra computation to find the length of the corresponding components of a scheme. So here the length is D. And the subvariety is just x not equal to 0. It's a line, a single line. So you get a single line counted D times, but that is equivalent, rationally equivalent to any degree D curve. Because the fiber over 0, 1, you just get the polynomial f of x naught okay. And now if you want to think about what this family, this homotopy looks like, it looks like you're squashing down, you're kind of squashing down a nice full degree 3 curve down thinner and thinner until it becomes a line, but counted 3 times in order to produce an actual subvariety, an algebraically well-defined object. So it's like okay, so now if you put all these clues together, if you put everything that we've said together, you get the following conclusion. Conclusion is that A1 is Z generated by the class of a single line. And we actually give the name of the class of a hyperplane in projective space. We give it the name H. The cycle class of a line. Okay, let's start using the language. The cycle class of a line. Which line? Any line, because any 2 lines are linearly equivalent. Go ahead and figure out a variety W that takes one line to another line. Okay, you get this free abelian group. Just all you need is lines. Every other curve, this beautiful cubic, is linearly equivalent to 3 lines. 3 times a single line, 3 separate lines, they're all linearly equivalent. Absolutely. Same exact argument, AC, will work in this case. In fact, this same squashing argument, where you take a variety and you kind of squash it to a plane of the same dimension, you're going to get a multiplicity. The multiplicity is going to be the degree of that variety, always. You can see a sketch of how to do that linear equivalence in the book. I'll cover it. I'll cover it when we, maybe Wednesday, when we do explicit Chow rings. But this is a sample of that. It's actually much more generally true. AC. How does minus 1? It's just a formal object. Math online problem solving is formal. It's a formal combination of these things. It's just negative L. All right? Good. So this is A1 and A0. don't, not, it's not like topology class. I'm not even joking. There are deep, unanswered, unsolved questions about a sub 0 of some of the most basic varieties in this world. Studying a sub 0 will take you, for random varieties, will take you to the edge of current knowledge. Okay, so don't gloss over a sub 0 like it's nothing. But in this case, it is stupid. It is equal to z times the class of a single point. 1 point. Which point? Any point. Okay, so what's the content here? Any 2 points? Any 2 points are linearly equivalent on P2. And now if you take, that's it, that's all you gotta, right? You gotta do cycles, mod, equivalence. So any 2 points are equivalent because you can take the line that joins them and think of that line as a W inside of P1 cross P2. Right, so I won't go through that. Any 2 points are equivalent because you got these lines that cover the whole variety that help you do that. Okay, but here's a question. What if it's not algebraically closed? What if it's not algebraically closed? A good question. Yeah. What if not algebraically closed? No, it's still okay. It's still okay. I believe it's still z adjoint 1 point. Here's why. So this is for Luo. Here's why. Here's why. See if you believe this. You might not believe it. So the issue is you might have some points that are defined over an extension, but they're Galois conjugate, right, Luo? But you can always pick another point and I think you have two options here. You can pick a point and a line. And these are rational, k-rational points. You can just pick rational point. And then you play that you do the following linear equivalence. You take a group of matrices. I don't know if this makes any sense to you, but you take this group of matrices. Fixes this. And then you take the limit as t goes to 0 or infinity. And that's defined all over your original field. And the limit of the scheme will be contained in L. I think you can do this. And then inside of L, you're just looking at polynomials that have, and then inside of L, you just have a degree d polynomial over your original ground field. But any one of those, you can take a family that just interpolates to the x to the d. Does that make sense? So now here, interpolate to x to the d equals. So as long as the flat limit argument is okay with you, then this will k-rationally bring your cycle to the d times a point. So anyway, Luo, you're in the wrong class. We're just gonna work over an algebraically closed field. Because most of the time I won't know how to do it perfectly. Because it's already interesting over C. No, it's okay. It's okay. Just be careful when you ask me that, because it might not be. And be careful of my answers. You have to go check yourself now. Okay, so the issue with Chow ring of singular varieties is that it's actually not the naive. Okay, the definition that one tries to use doesn't work to define a cohesive product structure. Now there are fancy things that you can do, which I have no idea how it works. There are operational Chow cycle rings that help you. That one generalization of it. Yeah, I don't know how to make the Chow ring a ring for an arbitrary singular variety like that. And we'll see an example of a singular variety where by the way, you gave me a curve, right? I actually do know how to define a Chow ring on a curve. Because you see, all you have for you is 0 cycles and then the full fundamental class. You actually don't have much of a reason for a ring, because you have the 0 cycles points and the full class. So the Chow groups are all interesting, or are always there for any variety. Chow groups. Chow ring, though, the ring structure requires something nice. Okay? And yes, the Chow group of a singular curve is interesting in the sense that the singularities give you some interesting non-predicted rational equivalences. Can give you rational equivalences that you might not have predicted. Yeah. So maybe I'll talk about the y squared equals x cubed example in the case of it's a complication in the definition of the Chow zero of that variety. That's a good example for Chow zero being interesting. Even though that curve, you might say, is just P1 with a small singularity, but Chow zero becomes interesting because of the singular point. So that's actually a good something that I might talk about. Y squared equals x cubed Chow zero. Yeah. All right. Enough. Let's see. What? Did anyone redeem anything that I ignored? Yeah. So LBW, the question for you is the question for that example is what is Chow zero? And you can do it for this one too, like. Yeah. So this is if you know what this curve is, yeah, this is z y squared equals it's Chow zero. It's what is a zero of this? These are puzzles. Okay. Now let's see. Any other questions that I missed? Intersection theory and perhaps suppose that you have U is a bilinear map such that f u v equals 0, then either u equals 0 or v equals 0. Yeah. This is a well-known yeah, Joe Harris is fond of this example as well, megalomorph. Yeah, I've seen this example as well. Hey, look at your emote. Yeah, I've seen this one before. Apollo Go. Oh, credits. What about credits? Yeah, it's a good one. AC. LBW. Mega. Twitch, let's go. This is a famous chess streamer. I had no idea. You're probably not here anymore. Apollo. Hello, welcome. Math online problem solving. Okay, who else? Luo. All the Australians. Bezou. Kappa, like a log. Okay. Did I miss anyone? That's pretty much everyone that I see while scrolling here. Okay. Skugget was here. All right. I don't think I can. For some reason, I can't do it. I don't know why. I lost the copy paste. I must have clicked something else. Oh no! Sorry, sorry, math online problem solving. All right. Okay. I don't know who you want to go visit, or if you want to visit anyone, really. Did I miss any? Thank you for all those follows, everyone. I was busy. Wow. 27 lines. You want to see the 27 lines, Luo? There you go. This is a cubic surface. Do you see the lines? If you notice, this is a special cubic surface. Because it has some Eckhart points, where 3 lines meet at a single point. And that's a divisor. Moduli space of cubics. So this is a codimension 1. Actually, it's got several Eckhart points, so it's a high codimension. Basically, it's codimension 4. Subset of cubic equations. But yeah, there you go. All right. Thanks for the follow. Who can we go visit, huh? Should we go visit, who's on? Hey, Mega, you on? Can I? No. We can go to one of our subs. You know, one of our subs streams. No, it's all right, Mega. Let's go to one of our beloved subs. It's no joke. They are subscribed here for some reason. It's because someone gifted a sub to them. But let's go to one of our subs. His name is Guma Hikaru. Guma Hikaru. Is that how you pronounce it? It's a smaller streamer. But yeah, subbed here for some reason. Yeah, it's smaller. Yeah, exactly. Alright, so go enjoy that. I'm sure he's having fun. Your comments will not be read at all. Guaranteed. Alright, but I gotta go. See you on Wednesday.